Okay, welcome everyone to tonight's meeting. Tonight we have a guest speaker, Paul LaRocque, who goes to Rexdale Alliance Church. And Paul was with us basically from the beginning many years ago when Hugh Ross came and spoke at Rexdale Alliance Church back in 2006. And Paul has been interested in Reasons to Believe since then. So he's read quite a few books. So tonight he's going to do his presentation called The Bigger History. So I'm going to pass it over to you, Paul. Go ahead.
Okay. Well, hello, everybody. And I want to thank you for the opportunity. I do have a couple of beginning statements, and that's this talk, I developed it initially, basically for a non-RTB audience. So for young people or, so on. So here I know I'm preaching to the choir, as they say. So bear with me on that score. And I developed this material, and then because I was intrigued by these books that I had found, and then I found out relatively recently that there was 3 talks on climate change in the fall of 2020, 2 talks by Mark James and 1 by Hugh Ross. So again, forgive me if there's some overlap there because I hadn't seen those before. So, all right. So a little bit about my career. I did my undergrad at St. Francis Xavier University in Nova Scotia. And it was in the middle of that undergrad period that I became a Christian. But I stayed on in physics and eventually got a doctorate in laser spectroscopy. And that's what brought me to Toronto, basically, and I've been here ever since. And then immediately after the doctorate, I joined Optech. It was a survey equipment company that specializes in LIDAR, laser radar. I went on to program management and executive level and ended up being there for 35 years in developing different kinds of LIDAR systems, atmospheric LIDARs for getting, detecting SO2, airborne mapping LIDARs, both for land and for underwater mapping. I fully retired in 2020, and now I'm a part-time pastor at Rexdale Alliance. So just a little thing about the LIDAR. So this is one of our big ticket items. That box you see there is about 1 cubic foot in size, and it puts out 1 million pulses per second. And for every single one of those million pulses, we send it out, we get the return back. By very sophisticated timing, we know how far away the ground is. We know from the scanning mirror what the angle was. We know from GPS where exactly the aircraft was. So even from a kilometer or 2 high, we can get the point on the ground within a few centimeters in the end. So it's quite accurate. In this picture here, that's not an image at all. That's a collection of points. It's a point cloud. It's been color coded for height above the ground. So you see the very farthest away is green, and then the nearest to us, so the highest, is red. And a very unique thing about our LIDAR is that we could, for every pulse that comes back, we could measure the intensity, the amplitude of the return pulse. And by so doing, we could shade the ground. So this is grass, and this is a walkway. They're at the same height, virtually, but you can see by using the intensity, you can get much more detail from the information. Another application, a neat one, was Airborne Archaeology. This is an article in 2019 in LIDAR magazine. Basically, way back 30 years ago, we found we could find the bare earth under trees because there were so many pulses going out. A lot would hit the canopy, but enough would go penetrate through the ground and come back that we could find the bare earth under a vegetated area, which is something that stereo photography could not do at all. So this place, the NCOM, they used one of our early systems. And in 2009, they had a detailed map of this area in Belize of 80 square miles, and they did it in 6 days because they were flying, over the area. And previously, it took 25 years to map 9 square miles. So this has revolutionized archaeology. There's still no substitute for boots on the ground, but to get a big picture map of the size of some of these civilizations, and some of you may have saw that the Maya they've now know that they're much bigger civilizations than they ever dreamed before due to airborne archaeology. We did some spaceborne work. We designed a LIDAR that went on the Phoenix Mars mission in 2008. And that LIDAR discovered snow in the atmosphere of Mars for the very first time. So it was very cool and very nice for a Canadian company to find snow in the Martian atmosphere. The most recent one I was involved with was the Osiris-Rex, and Mike Daly gave a great presentation a few months ago about this. But we were responsible for designing the OLA, the LIDAR altimeter for Osiris-Rex, under contract to MDA. So we're quite proud of that. It launched in 2016. It collected samples in fall of 2020. It's left Bennu now, the asteroid, and it's going to return in the fall of 2023. And so in some of the early mapping, they had to find a flat area to try to touch and go, to try to grab the sample. They wanted to find a very flat area. And to their immense surprise, it was much more rocky and rough than they ever imagined. And so the LIDAR measurements were key, plus a lot of camera images, and finding the best place to try to touch, just go down, grab a sample and return. So, and this asteroid's about the size of the Empire State Building. And because of all the map, it's probably the best surveyed object in the entire solar system because of it's been mapped so thoroughly in the many months that this occurred. So anyway, that was one of the last cool things I did at my job. So anyway, so go to big history. I heard this term a few years ago and I was really struck by it. What the heck does it mean? I am a big history fan as well as being a scientist. Well, basically it's a discussion of us and Earth from the very beginning of time. They coined this term big history to talk about that extensive period of time. And 2 recent secular books, Walter Alvarez wrote the one on the left in 2017, A Most Improbable Journey, A Big History of Our Planet and Ourselves. And David Christian has been involved in big history for a long time. He wrote that one in 2018. Walter Alvarez, he's the author of the first one. He's one of the geologists. He basically proved the cause of the dinosaur extinction 66 million years ago. It was a big mystery. People argued back and forth what actually happened, but they conclusively showed that it was this massive asteroid that landed near Cancun, Mexico. But in this book, he basically outlines all the events in our history that just makes our present existence very improbable. David Christian's a professor in Australia, and he also takes a big historical arc. And he talks about 8 major turning points or thresholds. at each of these points, more complexity arose. So let me go into that a little bit. So these thresholds, of course, the first one is the Big Bang. And then the stars, matter coalesced and stars started lighting up. Then new chemical elements, and we know, of course, that's from supernova explosions in the cycle of the stars. And then 4.5 billion years ago, Earth in the solar system. And then the very beginning of life on Earth, that's threshold 5. And then threshold 6 for him is collective learning, when mankind started having culture and had the ability to maintain knowledge beyond a single person. It's a way to preserve that knowledge base so that you can improve upon it, basically. And then agriculture, threshold 7. And then the modern revolution, which is basically the Industrial Revolution. I guess another word for that. So these are the 8 thresholds that David Christian identifies. But he admits that, you know, the natural course of events is to disorder. How does, you know, so, and he admits this in his book. If there's a bad guy in the modern origin story, it is surely entropy, the apparently universal tendency for structures to dissolve in randomness. And I love this phrase, entropy is the loyal servant of the second law of thermodynamics. So how does this complexity arise by itself, given entropy? Well, interestingly, David Christian brings in the Goldilocks condition. And of course, that's that everything has to be just right. And he claims that it has to be a precursor to each of the thresholds that he identifies. So he talks about the ingredients, that new forms build upon the previous forms. But having the right ingredients isn't enough. The conditions also have to be just right. And those two give rise to a new complexity. And he uses the word emergent there, that they'll come up with emergent properties that are unlike the previous ones. And Alvarez, but of course, let me go back for a second. So, but he can't explain. David Christian, he's you know, they don't bring God into this at all. He doesn't have any explanation for how these just right conditions came about. And Walter Alvarez himself, he talks about the improbability of our journey here on Earth. And he says the astonishing revelation is just how unlikely our present world is. They could have led to totally different results, to a completely different human situation, or maybe a world with no humans at all. But Alvarez, he had to resort to wonderful tricks for things to work out just right for us. The first trick was the making of stars. Second trick was the synthesis of new elements inside the stars, supernova explosions. And well, the third, I'm sorry, yeah. So, and basically he talked about Christian's first 4 thresholds, ending with the formation of the Earth, the solar system. But again, he just states how improbable this all is. And even the Earth, As we know, the universe itself is made up of mostly hydrogen and helium, the two most simplest elements. But somehow our planet Earth is mostly composed of these four elements: oxygen, magnesium, silicon, iron. And two of these, silicon and oxygen, they basically make up silica or quartz. It's actually the second most common mineral in the Earth's crust, silicon dioxide or quartz. I was curious about the first one, and it's actually this thing called feldspar. I'm not a geologist. I like reading about it, but anyway, feldspar is the most common in our Earth's crust. And quartz was extremely important in our civilization for early stone tools and making of glass. And of course, it's crucial for silicon and computer chips, which is in a big shortage these days for the making of cars and so on. Threshold 5 for David Christian is basically the beginning of life, and still a mystery how non-life became life. But an even bigger step to Alvarez is the going from single-celled organisms to multi-celled organisms about 600 million years ago. And Alvarez says that this may be a very extremely improbable step. And it's been argued that although single-celled life may be common in the universe, multicellular life may be very rare. So again, what makes this happen? Well, the conclusion of these two secular books is that we've been very lucky. And they basically say that because we've been blessed with this good fortune, we should take better care of the earth because it's arranged so many good things for us in history. But that's about all they can say. So that comes to the title of my talk, A Bigger History, because as Christians, we have a God who is eternal, and he's goes back farther than just 13.8 billion years, which is all that the secular authors had to go with. So we have a bigger history. And I next want to talk about a book by Hugh Ross. He published Improbable Planet in 2016. And unfortunately, you can see it predates these other two authors, but they don't reference it. They don't mention it, unfortunately. But Hugh Ross also shows how the present conditions on our planet are just quite amazing. He talks first about where our planet's located in the galaxy, our own solar system, and I think to a lot of the audience here, you're familiar with these items. One thing that struck me was the habitable zones, and generally people focus on liquid water, that any habitable planet has to be just the right distance from its sun so that liquid water can be on the surface of the planet. So that's generally what the first one people say. And of course, Earth is just the right distance for us. But Hugh Ross talks about 7 more zones of habitability. The second one being just the right amount of ultraviolet radiation. The third having just the right conditions for photosynthesis. And you can see these various parameters that have to be just right for photosynthesis to take place. fourth one is the amount of ozone, because it protects us from the ultraviolet. Rotation rate of the planet to maintain clouds in the atmosphere. The tilt of the planet's rotation actually is key. The prevention of tidal locking of the planet, which of course, you know, in our own solar system, Mercury is tidally locked. And even the solar wind strength to protect us from cosmic radiation. So our Earth is in just the right place, and it has all these and more habitable conditions. Now, many exoplanets have been supposedly found now, about 5,000 is the latest number I found. However, less than 100 of these are estimated to have liquid water. And as we've seen, liquid water alone is not enough. Many other conditions are needed. So even though the number 5,000 seems like a big one, and if you talk to some people, they believe life is guaranteed out there because of just the incredible number of planets and stars. But having all those just right conditions, well, that's another story. So another condition for life is actually plate tectonics. It was only proposed about 100 years ago, and it was first ridiculed when they first came out with it. And it was only about 50 years ago that it became widely accepted. And for life to endure, Hugh Ross states that the planet must have movement of the plate crusts. And the driving engine for plate tectonics is the heat from these long-lived radioactive isotopes. Uranium, thorium, for example, these have billions of years of half-life, basically. So, and again, just as the Earth has those four major elements I mentioned, it also has abundance of these elements that give us the interior heat flow that provide the engine for the tectonic plate movement. He talks about the first almost 2 billion years in his book, that it prepared the way for much later advanced life. Minerals are multiplied, ores are transformed, enzymes were made, and this period provided an incredibly reservoir of fossil fuel resources, which we've enjoyed for the last 100 years, 150. That's another whole topic in itself. And all the photosynthetic life resulted in several oxygen sinks in the Earth, and that made possible the existence of animal life. I was interested to see that, you know, common dirt, we can take it for granted, but Ross claims that it may well be humanity's most valuable resource. So it took plate tectonics in a very, very long time for dirt to exist all over the Earth. He has this term called BSC, biological soil crust, and it's a blend of these things that are listed here. And from about 2 billion years ago to 600 million years ago, this biological soil crust, it created extensive soil coverage on all of the Earth's land masses. And it was only this that made possible plant life. And then plant life was exactly what land animals needed for their existence and survival. So it all just links together. Explosions of life in the history of the Earth, several of them. And these billions of years led to an, as he calls, an enormous treasure chest of biodeposits. So these are the fossil fuels I mentioned, the reservoirs that became available to us through these billions of years of activity. As far as life is concerned, there was they call it an Avalon explosion at 575 million years ago. And then I guess the most famous one is the Cambrian explosion of life at 540 million years ago. And Ross says, 50 to 80% of the animal phyla appeared within no more than a few million years. And I like this quote: "To say that scientists were and are still astounded by what the Cambrian fossils reveal would be an understatement. Numerous books and research papers convey their profound amazement for this Cambrian explosion of life." Again, something that's hard to explain on just a secular level. In the history of the Earth, there's been some major mass extinctions. Let me try to explain this graph, which I found, which is quite interesting. So here's the Cambrian explosion at 540 million years ago. And you can see the number of animal families growing. But then we end up with the first major extinction, the Ordovician, 440 million years ago. 50% of the animal families disappeared. So you can see the shrinking of the width corresponds to the percentage of loss of animal families. And then things grew again up until the Devonian, 30% loss. Things grew again up until the Permian Extinction, 250 million years ago. And that's the biggest one, 60% of animal families. And it's sometimes called the Great Dying, the Permian Extinction. And actually, there's a recent paper just this year that the author tells a convincing story that they think that it might have been caused by a rapid increase in carbon dioxide in the atmosphere as a major factor in the Permian extinction, which of course is relevant to us. And the next one is the Triassic, 200 million years ago, 35% disappeared. And then the Cretaceous, 66 million years ago, and that's the one that ended the dinosaurs. So you can see Earth is it's quite a violent history as far as extinction go. And it was, as I said, the Cretaceous extinction that took out the dinosaurs, who were the dominant life form on the planet. And it was a mystery for a long time. And it was Luis Alvarez, who was actually Walter's father. Luis Alvarez won the Nobel Prize in 1968, actually. But along with his son Walter, who wrote this book, it was around 1980, they developed this theory that they were wiped out by an asteroid impact. And as I said, it's now accepted that a rock the size of 10 to 15 kilometers struck the Yucatan Peninsula, releasing tremendous energies. A key piece of evidence for their theory was this sedimentary layer all over the world that had iridium concentrations many hundreds of times greater than normal. And it's they call this the CKT or the KPG boundary layer. But it's essentially this massive asteroid was composed of a lot of iridium. In the explosion, it went all over the Earth and created this thin layer of enhanced iridium. So that's how they believe they proved this. And small mammals did coexist with dinosaurs, but they were small. And Walter Alvarez, I don't think he mentions God in the book at all, but he does say it took a kind of a God in the machine, Deus ex machina, to get rid of the dinosaurs. And that's another one of his tricks that nature played in order for us to be here, was this massive asteroid strike. And Alvarez goes on to say, reviewing the history, the ancestry of our human bodies again brings us face to face with the improbability of the human situation. So I'd like to go and talk now about Hugh Ross's Improbable Planet. He discusses the last 2.5 million years, which is called the Quaternary Period. And there have been several ice ages in the history of the Earth, but it's only been cyclical in the last 2.5 million in the Quaternary. But only in the last 800,000 years did it take on about 100,000 year cycle. And this, having a longer ice age cycle, is essential for the survival of a large, globally dispersed, technologically advanced human population. If the temperature was bouncing up and down, at a very short time scales, then not much would it be able to happen. So, and Hugh Ross talks about 5 nearly simultaneous triggers for getting the most recent ice age. He talks of saying current, but I guess the most recent ice age to come into effect. So I'll talk about these briefly. So basically, the first one is, as we know, as the tectonic plates moved around, then the land masses moved around the globe. And what happened is that the Arctic Sea became encircled by land. And that prevented any thermal waters getting there, and it caused the forming of the polar ice cap. And on the South Pole, Antarctica moved to be on the South Pole of the Earth. And it isolated Antarctica from most of the warmth from the global oceans. So that was the second landmass that was a big factor. And then until about 5 million years ago, North and South America weren't connected. So this Isthmus of Panama between our two continents, that was about 5 million years ago. And what that did, it closed off ocean currents moving between North and South America. And it helped to set the stage for glaciation to occur. That's copy of an image from an article about that. Another thing that happened was the Greenland moving north resulted in a massive ice buildup on that land mass. This ice reflected the sun's energy, cooled the planet, and I've heard Greenland being referred to as the ice cube of the Earth. And some of the, is getting back to my career, there was some very seminal work done with GPS, in the early GPS technology, where they were mapping the ice coverage of Greenland over time with airborne LIDARs and the very early GPS technology. The last of the five was the rise of what's called the Tibetan Plateau. And so the colliding tectonic plates, which, you know, responsible for the rise of the Himalayas, well, it raised the whole Tibetan Plateau to 4,600 meters. Because of that altitude, permanent ice formed there. And because of its low latitude, where the sun's rays are hitting it more directly, much more of the sun's heat is reflected. So in the book, just quoting Ross again, given the sun's current brightness and the abundance of greenhouse gases, nothing less than the simultaneous tripping of these five triggers could have launched the Earth into an ice age. So again, we have these things happening for our benefit, which are, as I say, the secular person would just say we've been very lucky, but we have another answer. Well, Hugh Ross expanded on his Improbable book, and he published this book in 2020, and he gave a presentation about it, and it's in one of the links there for the RTB sessions. So it has even more detail about the climate history and its ice age cycles. So now I want to talk about temperature. So we're going to take a macro look first. From 550 million years ago to the present. So the scale here, the 0 point on this graph, is about 14 degrees Celsius. So just remember that in a lot of the graphs to come, the 0 point is 14 degrees Celsius, so it's not freezing. But you can see that the change in air temperature really changed a lot over the entire history of the planet Earth. Okay, let's zoom in to the last 5 million years here. Look at that in more detail. So 5.5 million years is on the left. And you can see that it's generally warm for about half that period. But it does have quite a variability. And at the start of the Quaternary, 2.6 million years ago, that's when the Arctic ice cap formed. And when ice sheets spread in the northern hemisphere. But at that time, the cycle of the ice ages was 41,000 years. Until about 800,000 years ago, there was a switch, and it switched from a period of 41,000 years to 100,000 years. So let's zoom in again now, getting closer to our present age. And this is all taken from ice core sediments in the far north. I did look at Mark James's presentation. I think he knows a lot more than I do about the science behind that. So I encourage you to go look at those talks from the fall of 2020. So the last 4 ice ages are shown here. It's 400,000 years ago. And again, this 0 point is 14 degrees Celsius. And you can see the pattern to the temperature variation. We're currently in what's called an interglacial period, which began about 12,000 years ago. The last interglacial was here about 125,000 years ago. And these numbers here, these are basically the last 4 ice ages. You can see the temperature was hitting about 14 minus 8, about 6 degrees Celsius around the whole planet. So these drops are basically, yeah, the coldest the planet has been in the last period, and that they are the ice ages. And I guess they define the ice age as when the temperature rose above this 0 point or 14 degrees C. So you can see that it does creep back up, but it didn't get above the 0 point. And that's why that's how they characterize these ice ages. Okay, we're going to zoom in again. So this is the global mean temperature before 10,000 years ago. So it's 90,000 to 10,000 years ago. And the variation is going up over a range of about 10 degrees Celsius. And the time scale for this change was a few centuries, sometimes even less. So tremendous variability from about 90,000 to 10,000 years ago. But if we zoom in again and look at the last 9,500 years, the variation from the graph looks like it's about plus minus 1.2 degrees. But if you actually do more detailed data analysis and account for other factors, Hugh Ross makes the point that it's actually more like plus minus 0.7 degrees. So over the last 9,500 years, we've had temperature variability less than plus or minus 1 degree. That's a huge contrast to what was happening before 10,000 years ago. And Ross makes this statement: it's stunningly anomalous, the climate stability, and far more stable than previously thought. For billions of humans to occupy Earth at one time, predictable, optimal climate conditions and patterns are essential. And Ross isn't the only one to reach this conclusion. Other papers, other authors have said the same thing. In this case, I found this on Wikipedia from a paper in 2001. It says the present period has been fairly stable and warm, but the previous one was interrupted by numerous cold spells lasting hundreds of years. And it goes on to say that this period of stable climate, which we now have, which allowed the Neolithic revolution, and by extension, human civilization, may have been possible only because of a highly unusual period of stable temperature. So it's echoing Dr. Ross's comments about this being very unique and unusual. There's quite a few things that influence the Earth's temperature. I'm not going to go into them. You can go into Hugh Ross's book or other sources, but there's about a dozen astronomical cycles. And all these factors have different periods to them, ranging from tens of thousands to millions of years. And there's other variables too, besides the astronomical ones. But all these things acting together, they cause this pattern that you see here. Remember that 0 is 14 degrees C. Whenever the temperature reached 16 C, an ice age would follow that would last 100,000 years. So it hit 16 C here, and then the Earth slowly cooled the planet. It came back up, and then it cooled again, and again, and again. So this pattern you would expect to just continue. However, something happened. After the last ice age, something unprecedented occurred. A brief but dramatic cooling period caused that temperature rise to stall, and that one uncharacteristic phenomenon changed everything for humanity. And this event is known as the Younger Dryas. I'm not sure where the term came from, but you see it's right here about 13,000 years ago. Everything was starting to cool, but then this event happened and the temperature rose back up and led to unprecedented stability after that. So why did this event occur? Well, it turns out there was a massive glacial lake in the middle of North America, Lake Agassiz. And about 13,000 years ago, a major breach of the ice dam occurred, and the outflow of all that cold water flooded the North Atlantic. It caused a cold snap that lasted for about 1,000 years. So you can see that the Younger Dryas was stayed flat. But after that, a unique stabilization of the global temperature occurred. But what caused this big outflow of this Lake Agassiz? Well, Hugh Ross and other researchers believes it was yet another asteroid impact. They call this the Hiawatha Event, and it struck the northwest part of Greenland about 12,800 years ago. So it's right here in the square. And by using ice penetrating radar, they found that the crater is about 31 kilometers in diameter, and it's buried under almost a kilometer of ice, but it's there. This is a science article from 2018, the image. So just to talk about these unique events. I mean, it's just amazing, the circumstances that, and even the secular historians agree that they're very improbable, but they occurred. And these include, the movement of the tectonic plates on the Earth, 2 significant asteroid strikes. But as Christians, we know these were just not happy coincidences, it was God's providence for us. Well, what about the future now? Let's talk a little more about temperature. Here's that cooling event, the Younger Dryas, that occurred, seemingly from that asteroid strike. And then we have this very stable period, although there are dips and peaks in it. For example, they have something called the Little Ice Age, which lasted about 400 years in the medieval time. But if you look at the global average temperature from about 1850 to 2020, you can see the trend. And what they've done is they've chosen the period from 1850 to 1900 as a reference. And that is 0 on this graph. And another name for it is the pre-industrial baseline, so before the Industrial Revolution. And that's the average from 1850 to 1900. And you can see that starting 1920 and onwards, the temperature just continues to rise. And if you put a 10-year moving average on it, basically in 2017, the planet was 1 degree above that pre-industrial baseline. And if this curve, extrapolate the trend, the projections are 1.5 degrees Celsius by 2037 and a full 2 degrees by 2063. And when you hear the people talking about climate change and the temperature increase, this is what they're talking about, is a degree rise above that pre-industrial baseline. Well, what are the effects of higher temperature? If it gets to 1.5 degrees Celsius above that baseline, it's likely that 70 to 90% of coral reefs will die worldwide. And they predict that if it gets to 2 degrees, 99% of coral will be gone. Extreme heat wave events, they're 9 times as likely if it's 1.5 C. It's 14 times more likely at 2 degrees. They say that if we limit it to 1.5 degrees Celsius, that could cut in half the amount of sea level rise that's expected by the end of the century. But even if it's kept at 1.5 degrees, there's warnings that storms, heat waves, droughts will be more severe. And this whole, the effect of this is very nonlinear. Every 1/10 of a degree makes things worse in an exponential way. Well, personally, I'm not saying that these climate changes are part of the end times. Scripture is very clear that only the Father knows when Jesus will come back. However, in chapter 25 of Matthew, Jesus does talk about the final judgment. Familiar words to most of us, I hope. For I was hungry and you gave me food. I was thirsty and you gave me drink. I was a stranger and you welcomed me. I was naked and you clothed me. I was sick and you visited me. I was in prison and you came to me. Truly I say to you, as you did it to one of the least of my brothers, you did it for me. So that's very sobering words in Matthew 25. And what we do know is that, for example, impoverished families in developing countries, they're the least to blame for man-made climate change. But they'll bear the worst of the impact. This whole slide is a quote from a World Vision article, How Climate Change Impacts Poverty. So prolonged droughts, withered crops, hurricanes, floods, landslides, more strife within families and communities, and more separated families as people have to be on the move. So what's our charge? In the first, in Genesis, oh, is there echo there? In Genesis, the first book of the Old Testament, God gave us a mandate to be faithful stewards of the earth. And in Matthew, the first book of the New Testament, Jesus tells us to look out for the least of these among us. So together, these tell us that each of us must do our part in minimizing climate change, being better stewards and better brothers to our neighbors. So in conclusion, you can see that whether one believes in God or not, the history of the universe and of the planet Earth, it's been just extraordinary circumstances and events for us humans to be in a resource-rich and a stable environment. But this privileged position we have demands that we act to be better stewards of God's gift of this planet to us, and to spread the good news of his incredible providence to us and his free salvation through Jesus Christ. Okay, thanks for listening. That's it. Thank you.
Thank you, Paul. Now we're going to have a Q&A. So if you want to ask Paul any questions, go ahead. Paul, maybe the first thing you can do is explain how you got that 14 degrees Celsius when the chart says 0 degrees.
Oh. It's just a reference point. No. So I don't know why they do this, but they chose as their 0 point on their graphs a 14C point. So I guess it just became a convention for people making these graphs that the 0, it was, I think most of these graphs were meant to be in a relative graph where the baseline was, anyway, that's,
I thought that's supposed to be a global average temperature so that, because of the winters and summers, the average is around 0 degrees Celsius. And you balance the cold of the winter with the heat of the summer, you get an average of 0.
No, I think if it was 0, we'd be in an ice age. So it actually, the average, I think the average is about 14C. Yeah.
Okay.
Yeah. Yeah. So I guess I guess the equatorial places are much hotter than we are cold. I think that's, yeah.
Okay. Anyone have any other questions? Unmute yourself and go ahead and ask your question.
I have a question. What about I mean, in the end times, aren't some of the 12 astronomical cycles going to be affected? Like, I mean, it's not going to be purely determined on ice age criteria, is it? For, you know what I'm trying to say?
Oh, well, if Jesus could come back anytime, and then all bets are off. All predictions
Yeah.
are off.
Oh, okay. All right.
Yeah,
Okay.
for sure. Actually,
Because my understanding is, you know, the solar and all those astronomical factors come into play. But anyway, okay.
oh yes, and
Yeah. All right.
Hugh Ross's presentation in the fall of 2020, he actually gives he comes up with strategies that he would recommend for minimizing the effect of temperature change, and he thought that we might get away with, I think most people believe that and you know, given Jesus not coming back, that another ice age will come. That's just the pattern of the planet. But he believes we could do things to keep it away for 1,000, maybe 1,500 years more before another ice age might descend upon us. So yeah, no, I recommend people.
Well, yeah, but I don't think humanity's going to last that long, are they? But anyway.
That's another question. Yes, you're right now.
All right. Okay, that's it. Thanks.
Someone named Moto G, it looks like you have your hand raised. You want to ask your question?
Yes, can you hear me?
Yeah.
Can you hear me?
Yes.
Oh, are you saying that because of climate warming that we're experiencing, that's keeping us away from the ice age? And if that were the case, isn't that good? Wouldn't you rather be that than being in an ice age?
That's a good question. I believe it's postponing the ice age, but I don't fully understand all these cycles but you saw on the graphs of the last 4 ice ages, anytime the temperature got to 16 degrees Celsius, it just started dropping over the next 100,000 years. So all these factors that determine the Earth's temperature were coming into play, and I believe they are still coming into play. But yes, our present situation, I think, is postponing the ice age.
But isn't that good?
It'll be good if it doesn't. I guess in all those previous ice ages, I think the peak of the temperature was 16 degrees Celsius, about 2 degrees above their zero. If we start getting, you know, if we hit 20 C as an average, that won't be good. So something on the planet tipped back to cold after 16 C. But if we keep going up and up and up, you know, we don't want to end up like the planet Venus, you know, which is a greenhouse gas planet, where, you know, there's molten lead on the surface of Venus because of all the temperature, the heat is kept in by the greenhouse gases on that planet.
Hugh Ross explained once why, when the temperature goes up, why it causes an ice age. He said that all the ice in the North Pole melts. Because of the heat, you get more evaporation. In the summer, in the winter, you get a lot more snow. You get like 5 times more snow than normal. So all that snow lands on the ground, and you have so much snow that it doesn't melt by the time the summer's over.
And it
so
reflects.
that you have more.
And it reflects the sun's
reflected
energy
it,
away.
and then the next year you get again more snow because the water, there's no ice in the North Pole. The water is warm, it evaporates a lot more, creates more rain, and which becomes ice in the northern part of Canada. And so you get way more snow falling because the ocean is not frozen. And eventually you get all the land covered in ice, and eventually the ocean will freeze, but I think you end up getting the snow lasting all year round, and that's why it reflects the light, and you don't have it starts to build up.
Yes. Okay.
So what caused the reversal of the ice age when the ice age come to an end?
That I don't know. I don't know. You never explained what that happened. What causes that?
It's a good question. Yeah, I don't know either. No. Something to look into. Yeah.
Paul, can you share your screen? There's one slide where you have the period of time from about zero, the year zero up to the present.
Zero.
Like over the last 2,000 years, even maybe only the last 1,000. There's something I want to ask you about that graph.
You mean on the last 10,000?
No, the last 1,000 maybe, or last 2,000.
Oh, okay. Let me see if this is the one. Is it this one here that you're referring
Share
to?
your screen first so we can all see it.
I have to push the button, yeah.
No, the next one after that. Keep on going. No more.
Okay. Oh, this one?
Right there.
Okay. Yep.
I think it's that one. No, keep on. Yeah. See this little ice age pattern here? The temperature that we have now, is that colder than this hot period before the little ice age?
Oh, yeah, they have this little peak here they call the medieval warm period.
Yeah, and even before that, like you have this really big peak way here.
Right. That's about 3,500 years ago or something, maybe, yeah.
So are they expecting that because of the climate change now, that the temperature will be as high as that, or will it still be less?
Yeah,
So it's two, so it'll be that high.
and these are temperatures in Greenland, actually. Just that was, yeah. It's not a global temperature. This particular graph is just temperatures over Greenland, and it's -20 Fahrenheit. Sorry, it's not in Celsius. I know we're metric here, but it was a good graph for showing, the relative recent history of the temperature.
Somebody's. Okay. Because it almost makes it look like as if we're not even going to reach that high level yet, or for many years. Because it almost implies that there was no coral at that point. If the coral is all going to die when the temperature goes up an extra degree here, what happened back then?
Yeah, I guess if this is 1450, and that's 1860 here. I guess I don't really have in between. Yeah. But as I say, it's kind of relative, because this is, in this graph, I'd have to get global temperature in that time frame. Yeah. Mm-hmm.
These temperatures that the ice ages that go back, 15,000 years ago, the population would have been a lot smaller. Mm-hmm. I guess people would have lived through these ice ages if humanity goes back 70, 80, 100,000 years ago, then humanity experienced these ice ages.
And I expect they would have moved to the equator, migrated away from the extreme cold. So they wouldn't have been in, northern Canada probably at all for.
It's just harder now because larger population, not everybody can fit into the equator.
Oh, exactly. Yes.
Yeah.
Yeah. Severe competition.
My question is, in Improbable Planet, there was a faint sun period. I just can't name how long ago that was, but the luminosity of the sun has been increasing steadily ever since then. It doesn't look cyclical. It looks like it's just going to keep going because just the what do you call it? The history of the sun. It goes one way. It's a fire that goes through certain periods. So projecting that, that would be one way of posing that question. When is the big cutoff point where life just cannot exist? And at the present trajectory, like you can say, well, life can only last another 100 or 1,000 years or 10,000 years. But it looked pretty steep on the graph, but graphs can fool you because it can be 1/100th of a degree, or it can be a whole degree or whatever. But you remember that part in Improbable Planet, I'm sure that graph.
Hugh Ross once made a comment that in 1 million years, the Earth will not be habitable for humans.
Okay, well, I won't be around.
But no, you're right, Andrew. That graph definitely was going up and up with luminosity. Yeah. And actually, I think Hugh Ross makes that another providential thing, that despite the incredible, like the sun has been most luminous now than it ever has before in its history, and it keeps getting more luminous, as you said. But yet other factors are keeping us from getting too hot.
Okay.
Yeah.
So there's counterbalances.
Yeah. Mhm. I think there was a question in the chat about whether the climate change is man-made or not, and I know that's been a big debate for a while. But as far as I know, I'm not an expert by any means, but I follow Catherine Hayhoe. I think she's a great scientist, a climate scientist from Texas, Canadian born and raised actually, but she makes a very compelling argument that it is man-made, that the temperature changes that we're seeing are due to our using up these fossil fuels that God had providentially prepared for us over billions of years. So, yeah.
So it begs the question, if God can offset an increasingly luminous sun with other things, then, why can't he off balance what man is doing with burning fossil fuels, etc.?
Yeah, I guess that gets into, if is God, like the previous cycles of ice ages seems to have always, balanced out kind of. But are we messing it up? Are we being such poor stewards of the planet that we're messing it up? And then is God going to fix that for us or not? I mean, yeah, that's a good theological question. He doesn't always save us from doing silly things. So, yeah.
Shag has a question.
Sure.
Oh, have you read any of the climate change deniers from Christian side, and how do you respond to them, to their claims?
Yeah, I have to confess I haven't. I'm not a climate scientist. I have interest in the area, and I have an interest in preserving the planet Earth for my grandchildren and future generations. So, but no, I follow, Catherine Hayhoe is a very strong Christian and a very respected climate scientist. So I like, I guess we all have our people we might go to, but she's one of mine, I guess. She makes sense to me. Yeah.
George, you have a question? George Reimer, you have a question? No? Go ahead.
Yeah, my question is in terms of how have you had opportunity to use this presentation in a non-Christian audience, and how has it been received, if so?
Actually, no, I look forward to doing so, Hilmar, but actually this is my first run through, and that's why I appreciate the feedback and the questions. I do want to present it to, maybe the young adults at our church or so on. But yeah, no, I haven't yet found another audience for it. And part, as we all know, part of the problem in Christian circles is getting over the barrier of an ancient Earth. I mean, Dr. Ross has made tremendous strides in that area, but in some more conservative settings, it's difficult to talk about these immense timescales without people not being happy about it. So, yeah.
That's probably why it's more appropriate for a non-Christian audience.
Yes. Oh, true. Yes. Yes. Yes.
Peony makes a comment in the chat. It's not really a question, but the graphs show major temperature fluctuations, like from 100,000 years ago up to 100,000 years ago. And I'm not sure what your question was, Peony, but yes, that is true. And people that were alive during that time had a very difficult time. In a previous talk that Hugh Ross gave, he mentioned that it was very hard to do any sort of farming with those wide variations of temperature, so that the people actually were planting about 5 or 6 different kinds of crops, because the temperature variation would probably kill 4 of those crops and only 1 would be left. And so they could only eat whatever the one is left. So it's very hard. And it also prevented, our modern civilization from rising, from growing. And it wasn't until the climate became stable that then you could grow crops and be pretty sure that you're going to get some food in the end. That's what enabled our civilization to grow.
Yeah,
So I don't know if you have any other question, or if that answers what you're asking.
Well, I think the question or comment might get to what, some people like the people who don't believe that humankind has caused these temperature changes, because there have been big fluctuations before the Industrial Revolution. But I think what I've read recently is that argument's, I think, over. I think scientists have the vast consensus is that humankind has caused the warming of the Earth. Yeah, it's not just a natural event that's happening.
Can you hear me now?
Yes.
Okay, sorry. I had to switch cameras. So I will play the devil's advocate.
Okay.
I'm not a climate denier, but I'm a climate skeptic. And I really like to hear both sides of the coin. And one of the things that has bothered me in the recent past, is when I've been researching the IPCC reports, that the IPCC has a mandate to reach consensus among its scientists, which is bothersome to me that that's one of its objectives. In fact, from my research into its definition of climate change by IPCC definition is that the climate change has to be defined as man-made climate change, which from what I've seen so far is that they will not accept or not give credence to any research articles that don't support a man-made climate change scenario. So that bothers me, that whenever anybody presents a research article that is not supportive of their mandate to reach consensus, it is not necessarily given the same level of credence or ability to add weight to the climate change discussion. So that's my first point, that bothers me, that we can't have it seems to me we can't have a real discussion about everything that's relevant to climate change.
And I agree with you, George. That's not good science.
It isn't.
That's not good science if you're dictating what the outcome should be.
Well, I looked it up. At first I didn't believe it, and I looked up their IPCC definitions, and yes, they definitely said in their whatever their papers were, or whatever their creed was, that climate change, quote unquote, capital letters, means man-made climate change, which means you can't take in other effects or other possibilities, other hypotheses, right? Which is bothersome to me, that you have to sort of eliminate or throw out any other kind of hypotheses right away, because I mean it makes perfect sense from their mandate to reach a consensus. So if you find something that doesn't support it, well, then you won't pay much attention to it. So that's one of the things. The other thing, I was just thinking, Paul, in your LIDAR studies, did you ever use PID loops, progressive integrated derivative loops, to maintain your camera, to maintain your sensor data?
What kind of loops, sorry?
PID loops, progressive integrated derivatives.
Yeah.
Doesn't that global warming, that global temperature curve remind you of a PID loop that's out of whack? It's like going up and down, up and down, up and down. It strikes me as like this is like something that needs to be fine-tuned. And maybe that's what we got for the last 9,000 years. Sorry, it's maybe an inside joke, but it's
interesting.
that's one of the things I'm seeing in that.
Okay. Yeah.
Paul, can you explain that? Explain the joke. We don't get it.
Okay, so in my in the work that I've done over the last couple of decades, it was in controlling cameras in their exposure rates. So we wanted to keep the cameras looking at their subjects. In our case, it was looking at roadways, highway pavement, and the infrastructure around highways. So we had to, as we were driving down the road, we had to keep our cameras as even as possible, so that as you went across a bright piece of pavement or a dark piece of pavement or sunshine, or even as the sun went down, you wanted to keep the camera exposure as even as possible. So we implemented these progressive integrated derivative loops so that your brightness error was fed back as a feedback loop into your current exposure, so that it would adjust based on the error and the projected integrate so that you keep the camera level. And basically what that means is that curve that Paul was showing about the temperature going up and down, that's what a camera would look like when you're driving down a road that was changing a lot. Like the levels of brightness would change a lot. So we're trying to keep them stable. And if you didn't keep your loop stable, it would flutter all over the place and it would get out of whack. And that's kind of what I see in that last 9,000 years. Suddenly something tuned in that loop so that the feedback system was stable. It's quite stunning, actually, that something happened there, right? That some intervention, so some alignment of whatever those.
Yeah, well, George, if you read Hugh Ross's book, Improbable Planet, you'll get a better explanation of how.
Well, I did read that, and that was one of the things that brought my attention to that. That's quite a good book. I really enjoyed that one, the Improbable Planet one. I have a further question, Paul. When you were doing your studying, did you come across anything about magnetic pole shifting or the Earth axis flipping? That there's a lot more. There's a lot more to the, as we can imagine. There's a lot more to the Earth's climate than we've figured out so far, right? And that's that's just the nature of science. That as we dig deeper, we'll find out more and more information. So I'm wondering if you came across any information along those lines.
I didn't, in this context, but I mean, I have read that, the North and South poles had flipped in our Earth's history, and that just boggles my mind. Like,
yes.
what caused that? How does that happen? So yeah. So obviously, there's more to figure out. What do the migratory birds do when that happens? What the?
Yes. Well, that's along the lines of that. Continental shift, right? Of the continents and moving around and such, right? Like what's the forces behind that? Because it seems like that's not very stable either. That those things move around. I think Hugh Ross talks about that in his book. That our current configuration of continents is not stable.
They're moving. Yeah, they're moving all the time. Yes.
Right.
Yeah.
And so that brings to mind, I just want to bring one more point up. That brings to mind Isaiah 24, where Isaiah talks about the earth shaking like a staggering like a drunkard, right? That the continents can shift and we will stagger like a drunkard when some of these things happen. So it's,
well, that's also what happens during an earthquake.
That also reflected the earthquake. That's right.
Yeah.
But if the continents are moving, if we get a flipping of the earth, if the earth axis shifts, as in some of these dramatizations, not dramatization, but demonstrations there was one from one of the Russian astronauts showed that there's I forget what the name of it is. Jan, maybe you remember the Debrinsky effect, I think it is, where something is it's unstable.
Yeah, I don't recall exactly. I haven't seen it for a while. Yeah. But what also I'm not sure whether the climatologists are taking it into account is what's happening inside the Earth, right? Obviously, there is the hot there is the hot internal huge mass with I don't know whether it's iridium and iron and this has a huge magnetic effect of a dynamo on the Earth because it's moving, right? It's moving, and so if this movement goes certain direction, it can impact many things. Like, for example, the magnetic fields. It can impact the axis, the shifting of the axis of the Earth, and obviously, if the reaction between the metals inside the Earth can go hotter and cooler, right? It could have a big impact on the climate as well, right? So yeah, it is a complicated system. I think with the 16 degrees, it's maybe this portion is comparatively easy to understand. It looks like the external climate has its natural way of keeping itself within a certain range, right? So when the average temperature hits the 16 degrees, then the ice caps on melt, and then it gets into this period when there is the high amount of precipitations, and then all of a sudden the snow starts forming again, but that it's at the cost of us getting into the climate cooling scenario, right? So there seemed to be some kind of a natural way of, okay, when the temperature hits the 16 degrees, then it starts dropping, right? When it gets to a certain point, when the coverage of the snow and the ice caps is big enough, then the temperature now all of a sudden goes up because there is less clouds and more deflection of the sun through the ice, right, on Earth. So this portion is comparatively easy to understand, but obviously there is the other things, that's the sunspots and the radiation from the outside of the galaxy, and I mean that's pretty.
Talks about 24 or more different factors that all come into play. So yeah.
Now concerning us here in the Earth, there is a number of factors that affect us as humans not doing a great job in serving the planet. Like, for example, because of using the wood for warming people up, right? We've caused lots of deforestation and the deserts, right? Now this can be reversed if instead of subsidizing the agriculture, which is focused on chemicals and on using the GMOs, if we could use the agriculture that would use the local plants to actually make more forests in the areas which had been deforested, and I think Hugh was mentioning it as well in the past. So by doing that, by putting more forest on the mass on the Earth, we would kind of capture the CO2 from the atmosphere, put it into the and at the same time we would be able to enjoy nice forests around, right? Or maybe even explore them more quickly, because we can grow them quicker than they would do it naturally, right? So
yeah, Hugh Ross made a point of one of his strategies was to, people are felling trees and deforesting areas in order to have fuel for cooking and heating. Well, give them free kerosene. keep keep them away from the forest. So I mean, yeah, I mean, in the long run, that, yeah.
And we know that in the Roman times, the northern Africa was, was a breadbasket. People were, were living there and having lots of food, and there was lots of plants and forests there, and gradually it just the Sahara moved because we made a lot of deforestation in this area.
Right. Yeah.
And maybe not kerosene, maybe nowadays it's liquid natural gas. That's hot topic right now, right?
I see. Okay. Yeah.
And if we want to subsidize agriculture, I mean, we should be subsidizing the way that brings the forests back, and that brings the local plants back the way they were, and they are actually growing typically with much less water than the extensive agriculture that requires lots of watering and lots of chemicals in order to have the plants grow.
Mm-hmm.
That brings up an interesting point, Paul, during your talk. One of the things that Hugh Ross talked about was that at some point, the glacial water from the Tibetan Plateau and from the Arctic and the Greenland, we would run out of that water. It will not be sufficient, like those major rivers from the various areas in the earth. We will run out of the water that it's supplying us with, and we won't have the water to irrigate our food supplies. That may be one of the tipping points as well for us to be able to live on the earth.
No, that's a big source of fresh water, right? Yeah, you're right. Yeah.
Like we have an example what happened in Great Canyon, right, with the Colorado River basically being used for agriculture, and almost Colorado, when it hits the ocean, there's almost nothing left, right?
Yeah. And the water going to, they've built Las Vegas was a desert.
Right.
And all the water being used to service places like that where, yeah.
Going back to the trees, if you follow the money in South America, there's a lot of very valuable types of exotic woods. And a lot of that has been sold off. And then of all the crazy things, they found that it's very lucrative to have cows. So they've taken away the trees, brought in the cows.
Follow the money.
Yeah, follow the money.
Oh boy.
That's a whole continent there.
And then one of the other tipping points is, as I believe it's as well in Hugh Ross's book, about the Gulf Stream. Like when the water temperature changes enough, the Gulf Stream going from the Gulf of Mexico up through the North Atlantic stops. It changes its flow, and suddenly the North Atlantic becomes even colder because the Gulf Stream is no longer supplying temperature to it, and that causes part of that freezing of the north part of the Earth, right? That we end up having a trigger point, like if we ever reach that point, if we see that the Gulf Stream, and I've actually been watching some of that. There's a really nice website called earthnull.org, earthnull.org, and you can look at the various aspects of the Earth current, like in a graphic form. It shows wind maps and temperatures, but it also shows ocean currents and shows you how well the Gulf Stream is doing. And it looks, I don't know, but I can see that would be one of my places to have a look at, to see where how well our Gulf Stream, how well our Gulf Stream is maintaining its flow of warm water up into the North Atlantic.
Yeah, the ocean currents are critical, and the changes of the land masses show that in our history, I guess, that yeah.
And I have to admit that it's doing well, because when I was in Scotland, I especially made a trip to the western shore in order to find out how warm the water was, and it was really warm. And apparently much warmer than I'm used to, like in the Baltic Sea, for example. In summer, it's like, yeah, it's cold until probably, yeah, the end of July. So
Okay.
yeah.
What time of year was that?
Let me see. Yeah, that was actually in June. I would say mid-June to late June, right?
Yeah.
That,
Okay.
yeah.
Yeah. Yeah.
Well, thank you everyone for coming. Next month, we may be able to meet in person, but if we do meet in person, we'll also be meeting online for people that still are not comfortable to meet in person. I'm just waiting to hear an answer from People's Church whether they're going to allow us to meet in person or not.
Okay.
So just watch your email for announcements about that.
Oh, that would be great. Yeah.
Well, thank you everyone for coming.
Thank you,
We'll see you
everyone.
again next month. Don Waller will be speaking about the resurrection, an updated version of his talk that he gave 2 years ago on the resurrection.
Oh, perfect. For Easter, yes.
Yeah,
Yeah,
Of course.
Great.
excellent.
Yes.
Yeah.
we'll see you all next month.
Okay.
All right.
Bye, everybody.
Thank you, Paul. Thank you, Bruno.
Oh, I have one more question.
Okay,
In-
quickly.
for the ice ages in the past, what was the cause for the climate warming that produced the ice age?
Pardon me? Oh, that.
Well, yeah, I'm curious now too, so I'll have to look that up. I actually don't know what I mean, it seems like the planet Earth doesn't go extremely cold and stay there. It doesn't go extremely hot and stay there. It has this natural cycle of all these factors, and so
It could be an astronomical cycle, right? Because it seems to be pretty consistently 100,000 years or 90,000 years. I don't know exactly.
yeah.
But there is some certain cycles of the precessions and wobbling on the wobbling of the sun in the galaxy.
But I think what our questioner is referring to is that it's like a slow curve down in temperature, but then it's a very sharp, relatively sharp rise up to 16C. So yeah, what causes that to climb so quickly? Yeah, it's an interesting. Oh, I'll have to look that up.
A follow-up question is, whatever causes that, or whatever caused it, isn't that still going on today? Whatever that is.
Well, I think that'll be part answer or a question for our grandchildren's grandchildren's grandchildren, because we're going to be on the other side of that one.
I'm wondering if it occurred with any of these extinction periods, because there were changes during that time too.
Yep.
Mm-hmm. Yeah.
It's a complicated thing. It's so complex.
The extinction period would create a huge havoc. It would be like, okay, half of the Earth would be molten or something like that. So that's kind of incomparable.
Well, and one thing that struck me about the Permian extinction was that it's relatively recently that they think it was a rapid increase in CO2 that caused that extinction. And that CO2 is usually correlated with temperature to some degree.
Right.
Yeah.
So when you're looking into that, see if the CO2 is a trailing number or a leading number in that.
Oh.
Is it positive or is it correlated?
Right. Okay.
Anyway, complex.
Yeah.
Good night, everyone.
Good night.
night,
Thanks,
Bruno.
Bruno.
Thanks.
Good night. Good
All
night.
right.